Well, hello, epidemiology students. This is your friendly neighborhood professor, Deonandan again. And as I noted, this week's live lecture has been canceled because I won't be around. So instead, you get a couple of videos, including a video I'll upload later on describing what the midterm exam looks like. In this particular video, we're going to talk about causality, how we think about whether or not one thing causes something else. Does an exposure cause an outcome? Is it not merely associated with that outcome? What's the difference? Well, a lot of things can have associations. Your height is associated with your weight, but they're probably not causal, at least not entirely. That's a bad example. I'll think of a better example later. In fact, I know I will because I have one in the slides. We're also going to talk about basic statistics today, just as a review. This is not a statistics class, but you can't do epidemiology without understanding the very finite, tiny, minuscule bits of statistics needed to get through the course. So first, let's have a little bit of a review. We talked about different study designs recently. The cohort study, I'll remind you, begins with the ascertainment of the exposure status, and we follow our population forwards in time to determine the outcome status. So the exposure status here would be whether you smoke or not, and we wait to see whether you develop lung cancer or not. Straightforward stuff. The direction of inquiry is forwards in time. It's prospective. The case control study, on the other hand, begins with the ascertainment of a disease status, the outcome status, and we look backwards in time to see what the exposure status was. So in this example, we start by finding some people with lung cancer. Those are the cases. We find some people without lung cancer. Those are the controls. And we determined whether or not in the past they smoked or not. How do we look back in the past? Well, we look at medical records, or we can just ask them. Clearly, there are biases implicit in both methodologies, but the distinction here is which gets ascertained first, the exposure status or the outcome status. Review. Cross-sectional study, exposure and outcome ascertained simultaneously. Remember, the cross-section happens right now. Right now in time, how many people are left-handed and how many are women, therefore the percentage of women being left-handed is this. We ascertain both simultaneously. And we use that for surveys a lot, or for prevalence studies. But surveys are almost always cross-sectional in nature. It's useful for things that don't change over time as well. I mentioned left-handedness, which tends not to change. I mentioned gender, which tends not to change. It can, obviously, given today's medical technology. But in general, these things are with you for life. The case control study, on the other hand, is when we ascertain the exposure status first. Sorry, let me say that again. We ascertain the outcome status first, and then we determine, by looking backwards in time, what the exposure was. And this is great for outbreak investigations, because if you're showing up at a picnic where a bunch of people have salmonella, they already have the disease. So you're ascertaining the outcome as soon as you arrive. And you have to look back in time to determine what the exposure was. Maybe the chicken salad. Then the cohort study. This is when we ascertain the exposure first, and we move forward in time to see what the outcome is. And this is fantastic for measuring incidence. In fact, this is our default type of study, the ones that we prefer the most expensive of these three for sure. But only with cohort studies can we determine incidence, because we are watching time unfold and seeing how many new cases emerge. This is kind of real data, not really, but sort of. Imagine a New England town where we're keeping track over the years when the drowning deaths occur and how much ice cream is consumed all those days. And we find there's an almost linear relationship between deaths by drowning and population consumption of ice cream. Clearly, this kind of analysis would lead us to conclude that we have to stop eating ice cream. Every time I have an ice cream cone, someone drowns. What's actually happening here, of course, is that on hot days, people are more likely to be at the beach, and on hot days, people are more likely to be consuming ice cream. So temperature here is a confounder that is creating an illusion of a relationship between ice cream and drowning. But this is where we get into the whole correlation versus causation debate. Clearly, ice cream and drowning are correlated. We see that on the graph. There's a strong linear correlation there. But one is not causal to the other. So how do we disentangle that relationship? Well, remember, we know that smoking causes lung cancer. Or do we? Or do we? We don't really, but we do. We do because a lot of research has got into it, but we don't really because we can never do a true randomized control trial. We couldn't do this, for example, where we make a bunch of people smoke for 20 years, and we make a bunch of people not smoke for 20 years, starting at age 5, and we see which ones got lung cancer. We can't do that because it's not ethical and therefore not legal, at least not in this country. If we could do this, we would find pretty strongly that the group that smoked for 20 years has a much higher incidence rate of lung cancer than the group that doesn't smoke. But not being able to do this makes us rely on other epidemiological tools to ascertain the causal relationship between smoking and lung cancer. So that ascertainment involves looking at a series of criteria. The most famous series of causal criteria were proposed by Sir Austin Bradford Hill, who died in 91, and he has essentially 9 items, a checklist of 9 things that he believes if you were to satisfy these 9 things, there's a very strong argument for a causal relationship. We call these the Bradford Hill criteria. In fact, many years ago, some epi students went out on Halloween dressed as the Bradford Hill criteria. That's how geeky and dorky our profession can be at times. So this is not the only way of approaching causality, but it's the most famous and the most used in my experience. So we're going to go over the Bradford Hill criteria for causation now. The first is strength. What does strength mean? That's the strength of the association. That could be something like the relative risk or the odds ratio or the effect size. We talked earlier in this class that the relative risk of a cohort study looking at smoking and lung cancer is enormously high, over 7, sometimes double digits, depending on the population. And that's an incredibly high relative risk. So in this sense, the strength of the relationship is strong. Mind you, the strength of the relationship between drowning deaths and ice cream consumption is also strong. But it's the first checklist. Great, we move on. Number 2, consistency. Do we find the same results everywhere we look? Is the observation reproducible? As you're probably aware, one of the hallmarks of Western science is reproducibility. If different people do the observation or the study, do they find similar results? If we reproduce these results in different populations, do we find similar results? If I follow 100 smokers in Canada and 100 smokers in England and 100 smokers in China and compare them to 100 non-smokers in each population, do I get similar relative risks? So if it's consistent, check mark number 2. Number 3, specificity. What does that mean? It means that it looks like this is the main, I don't want to use the word causal, but the main factor that is strongly associated with the outcome we care about. So the smoking and lung cancer one. Okay, it seems like every time people smoke, or a population smokes at a high degree, lung cancer rates go up. Is there anything else that might be causing that effect? Are they living near smokestacks? Are they taking large amounts of benzene? Is there a genetic predisposition? So if we can rule out to some large extent the significant role of other factors, we say that this relationship, this outcome, is specific to this exposure. It doesn't have to be perfect, but it helps. Next criterion, temporality. And this one is fairly obvious if you stop and think about it. The cause must precede the effect, right? So you don't get lung cancer first and then start smoking. You started smoking and then got lung cancer. So if you can show that the exposure you care about started before the outcome you care about, that's another check mark in our list of things that convince us that there might be a causal relationship. Next is a biological gradient. That's essentially a dose-response relationship. What that means is if you were to smoke 2 packs of cigarettes a day versus 1 pack, does your risk of getting lung cancer increase? If you smoke several packs of cigarettes per week versus having a cigarette once every few weeks, is your risk of lung cancer heightened? And it is. So in other words, the more exposure, the more outcome. The less exposure, the less outcome. So if we observe that dose-response relationship, we call that a positive biological gradient, and that's another check mark on our list of causal factors. Now, sometimes it's not required. I mean, a single dosage sometimes of something is more than sufficient to give you the outcome. So with all of these criteria, you don't need all of them, but it helps. Oh, it looks like my Google Calendar just popped up. All right, put that away. Next, plausibility. Is it plausible that this relationship is real? Does it make sense biologically? In other words, do we have a theoretical framework within the science of human physiology to show that possibly smoking causes lung cancer? And we do, right? We know there's something about, the nicotine affects the metabolic pathways and cell health in certain ways that lead to cancerous growth. Okay, so we need that theoretical framework. We don't need it, but it helps. If your argument is that it magically manifests as cancerous cells, then your argument is weakened. So if you have a strong, biological, plausible, theoretical framework for explaining this causal relationship, one more check on the list. Next is coherence. What does that mean? It means that what you observe at the population level or at the human level is consistent with what we saw at the laboratory, tissue, and cellular level. Right? So the science is consistent throughout the gradient from cell to tissue to organ to person to population. Next is experiment. Well, if we could do an experiment, we wouldn't need Bradford Hill's criteria. But sometimes we do experiments on animals. So if there is evidence in the animal literature, then that strengthens our assertion that there is a causal relationship. And analogy. What does that mean? Well, that's a difficult one to explain, but essentially we're saying it works like similar things. We can say, well, smoking causes cancer the same way that radiation causes cancer. It has a similar metabolic pathway, has a similar tissue assault pathway. Right? So if you can make those sort of hand-waving arguments showing that we know these other things act in a similar way, so why wouldn't this act in the same way? That helps a lot. So those are Bradford Hill's 9 criteria, and I worked through the smoking example with you. Again, you don't need all of them, but if you do, it's a very strong argument put forth to convince people of a causal relationship. And these arguments were made in court when cancer patients were suing tobacco companies for having given them cancer through pushing of smoking products. Now, when we talk about causal relationships, there are 4 possible logical relationships that we can talk about in terms of a exposure outcome process. First is that the exposure is necessary and sufficient to give you the outcome. The second is that it's necessary but not sufficient. The third, the exposure is sufficient to give you the disease but not necessary. And lastly, the exposure is neither sufficient nor necessary to give you the disease. What does this mean? Let's work it through. First one, necessary and sufficient. Consider the example of the coronavirus. This is the virus that we know now causes the disease called SARS. So you can't get SARS without the coronavirus. You can't get the coronavirus without getting SARS. So the coronavirus is necessary to give you SARS, and you don't need anything else to give you SARS. That's all you need. It is both necessary and sufficient to give you SARS. Cool? Next example. Necessary but not sufficient. So consider any number of diseases that have a combination of a genetic predisposition and some kind of environmental trigger. I can't think of one off the top of my head, to be honest, but frankly, probably most diseases are like this. We all have a predisposition, like a predisposition towards heart disease. And the environmental trigger might be eating too much fat in your diet. Right? Like some people can eat a lot of fat and have no problems. Other people eat a lot of fat and suddenly are dropping cholesterol in their arteries like nobody's business. So, in this case, to get the disease, the heart disease, you need both of these factors. Both of these are necessary. The genetic predisposition is necessary. The dietary fat is necessary, but neither one on its own is sufficient. So if you look at this first factor, the genetics, it's necessary, but it's not sufficient because it also needs its pal, the environment. And similar to the environment, you need it to get the disease, but it's not sufficient. It needs its friend, genetics, to give you that disease too. Next one is sufficient, but not necessary. Alright, this one is a bit more straightforward to understand. Consider any number of cancerous diseases, let's say leukemia in this case. Right? You can get leukemia in many different ways. Radiation, for example, or benzene poisoning, or any other kinds of carcinogens you can be exposed to. So each of those carcinogens is sufficient to give you leukemia, but they're not necessary because something else can give it to you. So radiation, is that sufficient to give you cancer? Damn straight it is. Do you need radiation to get you cancer? Nope, because you can get it in other ways too. So it's sufficient, but not necessary. Still with me? Cool? Right on. Next one. It is neither sufficient nor necessary. And this, I believe, is probably the case for most things in life. Life is complicated, and interactions between exposures are happening all the time. So consider prostate cancer. So prostate cancer, you need hormones, you need a certain diet, you need an inflammation response. It affects only men, right? So each of these in turn is, well, a combination of these factors can give you prostate cancer. So no one of them is necessary, and no one of them is sufficient, but any combination of 2 or 3 or more can get you that disease. Right? So anything involving a complex interaction describes the neither sufficient nor necessary relationship. Cool. So just get those 4 types of relationships straight in your mind. Moving on now, let's talk about statistics. And I don't want to go deep into stats because nobody likes stats, even though it's magical. It's magical and philosophically wonderful. I'll just go over the basics. So first is what we mean by measurement. Measurement is assigning a quantity to a quality. Your quality could be agedness. How do I measure agedness? Number of years since you emerged from your mother's birth canal. Maybe the quality is size. How do I measure size? Well, I can choose to measure height in centimeters. I can measure girth in centimeters. I can measure weight in kilograms. I have lots of options. Maybe I'm measuring the quality of happiness. How do I do that? I assign a number to happiness. Maybe I'll interview you and give you on a scale of 1 to 5. How happy are you feeling today? So every time we measure something, we attach a value to it, and we lose a little bit of nuance about what we're qualitatively trying to measure. So when we measure, we assign a variable to that measurement. And we've used this word variable throughout our entire career, right? In math, a variable is something that changes within the scope of your problem, right? Y equals mx plus b. As we change x, y changes as well. So math, we would designate our variable with a letter x. In research, a variable is a logical set of attributes, like gender, age, socioeconomic status, height, whatever it might be. Right? Usually a word is associated with it, age in this case. In computers, variables are a symbolic space where a value is loaded into computer memory. A string, for example, would be an alphanumeric variable that saves a space for a number or a letter. When we create a variable, there are 2 components, the conceptual component, or phase, and the operational component, or phase. So think about a variable as a bucket, a container for holding information, but the variable is not the information. The example I used earlier of happiness, the information is happiness. I want to determine how happy you are, and to do so I create the variable called h, and h is a scale of 1 to 5, where I ask you, on a scale of 1 to 5, how happy are you right now? And you say 4. And your friend says 4.5. And your other friend says 3. Great. So I've got these numbers. These are buckets for containing and describing happiness. But they are not happiness. You see my point? Happiness is something a lot more complicated, having to do with your cortisol levels and your sense of well-being and your optimism for the future and maybe the quality of your relationships. And I've asked you a very simple, limited question that attempts to be a proxy for what I really mean. So every time we assign a measurement or a variable to a quality, we lose wisdom. We can never do this perfectly. That's the conceptual nature of variable definition. All right. So the concept of happiness is complex. I operationalize that by creating this thing, this bucket called H, with a score of 1 to 5. We do this in research all the time, and we need to remember that when it comes to interpreting our results. Now, there are two general flavors of variables: continuous variables and categorical variables. Categorical we also call discrete. So a continuous variable, things like age, height, distance, pure numbers where there's value in between. I can compute means on them. I can divide them and multiply them. Right? It's a natural number. We understand what that is. A categorical variable, on the other hand, is a group, age group, gender. Here I've got number of siblings. That's a bit confusing because that's a number as well, but you can't have 2.5 siblings. Right? What country you were born in, what is your race? Those are categories. They aren't pure numbers. So the most common type of categorical variable is a dichotomous variable. That means having 2 levels. So do you smoke? Yes or no? That's dichotomous. Do you have lung cancer? Yes or no? That's dichotomous. What is your gender? Well, we say male or female. Yes, there are more genders now, but in general, male or female. Right? So dichotomous is easy because we think in dichotomous fashion. If you are lining up to get into a club and I want to know your age, I care about, are you over 19 or under 19? That's what I care about. If you pull you over for driving a car, we check your license for your age. We care about, are you under 16 or over 16? We dichotomize everything in society. So dichotomization happens naturally in population health statistics. We can dichotomize things, meaning we convert something to having 2 levels. For example, if I have the age of everybody in the class, somebody's 19, somebody's 21, somebody's 25, some old fart in the back is 52, whatever, I can convert that. Instead of having a variable that says your age, I can create an age group variable that says, are you under 18 or are you 18 or over? Why would I do that? Because that's sometimes what I care about. I care about, maybe you're at the voting booth. Are you legally able to vote? Then I care about it if you're over 18. I don't care exactly what your age is, only that you're over 18. When we dichotomize, we lose information though. So if I go from knowing your age to simply knowing if you're over 18, I can't go backwards. If I know that you're over 18, I don't know what your age is now, unless I ask you. So every time we go from a continuous to categorical, we lose information. There are various levels of measurement, and this is a system of classification of variables. Right? So there are 4 types: nominal, ordinal, interval, and ratio. And you've covered this in your previous classes before. Nominal, let's go back for a second. Nominal measurements are names. You can't rank them. So what province were you born in? Alberta, Ontario, Quebec, whatever it might be. Each has equal value. I can't do a whole lot of math there except to count the number of people from each province. Ordinal means it has order. What order I can rank things. For example, how did you rank this class? Excellent, adequate, less than adequate, horrible, or atrocious. Right? That's a ranking. But I don't know the distance between excellent and adequate. I don't know the distance between adequate and sufficient, and between less than adequate and excellent, whatever I said. So I know the rankings, but I don't know how far apart they are. They could be differently far apart each time. I don't know. And that limits the kind of math I can do. With interval and ratio, these numbers are the regular numbers that we know and love, continuous variables. The difference, though, is that ratio has a rational 0 and interval does not. What's a rational 0? A rational 0 is when the 0 has something reflected in reality. The example I always give is degrees Fahrenheit versus degrees Celsius. So 0 degrees Fahrenheit means nothing. Freezing in Fahrenheit is 32. Right? So 0 is 32 below freezing. What does that mean? Nothing. Whereas 0 in Celsius, that has a real physical meaning. That means that's the temperature at which water freezes. Or height. Height is rational. If you're 0 centimeters tall, that means you're flat. You're a shadow. That's a real thing. If you're negative 5 centimeters tall, that means you're hanging upside down from the floor. 5 centimeters. Right? So that's what a rational 0 is. So ratio has a rational 0, interval does not. And these are the kinds of math we can perform. Nominal, all we can do is count. With ordinal, we can know the sizes of things. With interval, we can do count and rank and add and subtract. With ratio, we can do everything. Cool. Now, let's talk about frequency distributions, which is the heart of frequentist statistics. Again, if this terminology confuses you, don't worry about it. It's not a stats class. I'm not going to test you on stats. I just want you to be comfortable with some things. Okay. Let's say there are 10 students in my class, and these are their ages. 18, 18, 23, 25, 22, blah, 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 blah. Those are their ages. Bunch of young shits. Damn, I envy you. I'm old now. Being old sucks. It's not fun. Don't get old. Stop right now. I can show their ages using a frequency distribution display method. And the two I'm showing here is a graphical one and a tabular one. So on this table, I have 3 18-year-olds, 1 19-year-old, 2 23-year-olds. Right? That gives me a sense of where people are. Or I can do a histogram and show, oh, most people are that age, the second most are that age, so that's the mode, right? That's a frequency distribution. The most common frequency distribution, or the most important one that we refer to in statistics, is this, the normal distribution. And the normal distribution shows us the number of people that have certain characteristics. Let's say this is IQ. Okay, so most people will have this IQ. Let's say it's 100, and that is the mean. A slightly less amount of people will have higher than average IQ. A slightly less amount of people have a lower than average IQ. An extraordinarily small amount of people will have a very high IQ, and an extraordinarily small amount of people will have a very low IQ. But this is what the majority is. So that's the normal distribution, also called the Gaussian distribution, or the bell curve, right? Why do we care about this? Because every human characteristic can be in some way described by the normal distribution. That's not to say that if I took the IQ of every person in the world and plotted them here, it would look like this. It's to say that if I took 25 random people and took their average IQ, wrote it down, I threw them back in the pot. I took another 25 random people and took their IQ, the mean IQ, wrote it down, and throw them back in the pot. I take another 25 people, compute their average IQ, write it down, and throw them back in the pool. And I do this a billion times, taking random selections of 25 people each and computing their mean IQs. Those means that I've written down, those will be distributed on this normal distribution. That's the magic of the normal distribution. We call that this distribution of the sample mean, something like that. I'm a little confused right now. It's called something like that. But this is the nature of something we call the central limit theorem, that says that the sample means of randomly selected samples will be normally distributed. If you don't understand that or care about that, don't worry. I'm not going to ask you a question on an exam about that. I just want you to understand this is what makes statistics so magical, at least for me, that we get that magical distribution if we have an infinite number of random samples. Right? So again, we have these samples, we collect the means for each one, and we distribute them on a normal distribution. And this, a deviation is a difference between a particular value in my sample and the mean of that sample. That's a deviation. A standard deviation is essentially the average deviation from all my scores. And we know that a certain number of standard deviations away from the mean gives me a certain percentage of my distribution. So about 2 standard deviations from the mean, 1, 2 over here, gives me about 95% of everybody in my sample. Why is that important? That allows us to say, well, if I do a study, and let's say I'm studying IQ, and I take the IQ of you people, of my genius 4th year epidemiology class. And I know you're geniuses because you were smart enough to take this class, so you're obviously smart and accomplished people. And I compute that your mean IQ is 120. And I compare that mean IQ to this distribution of the population, and I find that you're over here somewhere, right? Because your mean IQ is greater than most people's mean IQs, right? That's great. But is it extraordinarily greater? Is it so much greater that you are very much different from everybody else? we know that you're more than the average, but is that extraordinary? And the question we ask ourselves is, what does extraordinary mean? Extraordinary really means beyond a certain cutoff on this normal curve. That's all it means. And we have arbitrarily decided that extraordinary means about 95%. Sometimes we say 99%. And you remember from your stats class that 95% means, well, a 5% type 1 error. We're going to go over type 1 errors later on when we look at sample size calculations. But the important part here is that we have arbitrarily decided that if you are above this cutoff here or below this cutoff here, you are extraordinary, to the point that you are statistically significant. You are significantly different from the distribution. Therefore, you are statistically significantly different. That's all statistical difference tells us. Our p-value lets us know where on that curve you are. Okay? What's a p-value? It's the probability that the sample, the IQ sample that I took from you, is actually typical of that distribution. Okay? So if it's low, if the p-value is low, that means there's a low probability that you are typical of that distribution. Therefore, a high probability that you are extraordinary. The important thing for you to remember really is this one thing, one simple thing. Ready? Here it is. If the p-value is low, the null must go. What's the null? The null hypothesis. The null hypothesis says there is no relationship. There is no statistical significance. But if the p is low, then there is significance. If the p is low, then there is significance. What is low? Well, we've decided that low usually is 5%. Sometimes it's 1%. But we decide that a priori. Okay? Fine. Last slide. The last slide, my friends, of this particular presentation is I want you to know some common statistical tests. You should have covered this in second year stats, but if not, the first is the t-test. And the t-test allows us to compare the means, the averages of two different samples. It was invented by a man named Gossett, I believe, who published under the name Student, just to confuse us, the same way the normal curve confuses us, because why is it normal, right? Student confuses us because his name isn't actually Student, his name was Gossett. But he worked for the Guinness Brewer Company, and he was comparing the qualities of vats of beer. So if we want to compare means, for example, if I want to know whether the mean midterm mark of this class is different from the mean final exam mark of this class, I will do a t-test. If I want to know, is the mean age of women in this class different from the mean age of men, I will do a t-test. Right? So if I'm comparing means, I do a t-test. Chi-square is when we are comparing categorical variables. We can't compute means on categorical variables. I can't compute means on, which country you're born in and, what gender you are, etc. I can count number of cases and do proportions, but I can't do means. So a chi-square allows us to test whether two categorical variables are associated. And lastly, a correlation. A correlation tells us whether two continuous variables are associated. Like what? Like ice cream sales and shark attack rates, or height and age, or income and BMI, right? So that's what correlation is for. So just remember, that's when we use these three tests, and you will be fine in this class. That is all, my friends. I will stop there, and there will be another uploaded lecture on the Kaplan-Meier survival curves for this particular set of uploads. Thank you very much.